Yeah, welcome to today's IFT research call. Today, Akshaya will present the libp peer-to-peer mix protocol, which we're researching and developing within the VAC ACC. Akshaya, the floor is yours.
Hello, everyone. I'm Akshaya from the VAC ACC team. Today, I'll be talking about enhancing privacy across libp2p using the mix protocol. So why do we need the mix protocol? There is no support for sender anonymity in libp2p, and this is where the mix protocol is designed to address this gap. And with mix protocol, it opens to a possibility of a wide variety of privacy applications within the libp2p ecosystem. It would enable us to add a layer of privacy for existing libp2p applications without actually changing their architecture much. It provides flexible integration, and it would allow us to build networks that are more resilient to surveillance and censorship. And the most important thing is it also enhances user privacy without relying on any centralized components. So in this talk, I will actually introduce the mix protocol, explain how it enhances privacy, and also highlight some of the key challenges that need to be solved. So before we proceed, I want to just say the scope of this talk. So first, we will see an overview of the mix, and majorly we will see how it differs from Tor, and then we will see what are the two major components of mix. And then we would see how to integrate mix with libp2p. And in that case, which components can be made pluggable. And then we would also see the major decision which we faced when we designed mix protocol, whether to design it as a protocol or a transport. And then we would also talk about reply mechanism using single-use reply blocks and known limitations that already exist in the mix protocol. And then we'll also talk about gossip sub integration, which is a work in progress, and the next steps. One thing which I wouldn't go into detail are the cryptographic concepts, because the focus is more on the practical side. So here is the mix overview. So let's take a simple goal. Alice wants to send a message to Bob without revealing her identity. So how she does this is she chooses random mix nodes and constructs a path through them and encrypts the message in the reverse order of the mix nodes and then sends it to the first hop. So each mix node in the path just removes one layer of encryption, and they would know which hop to forward this packet to. So each mix node only knows the previous hop and the next hop. They do not know anything else about it. So this is similar to onion encryption that we see in Tor. So how does it differ from that? So the path that I talked about is constructed per message. It's not like a direct connection that exists between Alice and Bob. So for every message, Alice constructs a new path by choosing new random mix nodes. That's one major difference. The other major difference is that mix nodes hold the message for some amount of time. We will see about this more in future slides, but they actually hold the message for some time. That is, they introduce some delay. So this actually provides strong protection against traffic analysis. And like I already mentioned, it introduces delay. So it's kind of mixes more tailored to high latency application. And how it differs from Tor. In case of Tor, there is a dedicated circuit established between the sender and the destination. And this circuit is bidirectional. So you could actually imagine it as a nested encrypted tunnel where the messages are being decrypted in layers in one direction and encrypted in layers in the other direction. And like I mentioned already, the nodes would not add in any delay. So it's more suited for real-time traffic, like instant messaging. But however, Tor is prone to probing attacks, traffic volume, and timing attacks at the endpoints, because somebody at the endpoints would be able to just correlate the volume of the traffic, and also the based on the timing, they can perform correlation attacks. So now that we have seen the difference between mix and Tor, we will go to the key components of the mix. There is two key components of the mix, which is the mixing strategy and the mix packet format. So mixing strategy, like I already mentioned, the mix holds the message for some time. That is, this process introduces delays to prevent timing correlation, so that it's harder to link input and output messages. And there could be many forms of mixing strategy, like batching, where it collects all the messages. That is, a mix node collects all the messages that's incoming, and then shuffles it and forwards it to the next node. Or you could have like a continuous time mixnet, where it just randomly adds a delay for each message from an exponential distribution. This second method is much more preferred because it has larger theoretically unbounded anonymity sets. In practice, however, like since the tail probabilities are really small, they could be clipped based on a threshold. But theoretically, it has larger unbounded anonymity sets, and it does more effective bandwidth usage, because in case of batching, all the messages are collected, shuffled, and forwarded. So a mix node would ideally like wait forever for a fixed number of messages to be reached. And the advantage about continuous time mix is that we would be able to fine tune the sparseness versus the anonymity trade-offs. We would be able to like tailor it using the mean of the exponential distribution. So that's another advantage of continuous time mix. So for the mix protocol, like we would go with the continuous time mixing strategy, since that has more effective bandwidth usage and like theoretically unbounded anonymity sets. And the next thing is like the mixed packet format. So the mixed packet format is the one which actually says what format the packet is once a mixed node processes it, what is the incoming and outgoing packet format is. Ideally, they should look indistinguishable. So weak packet formats can leak information, example, path length, position of path, or they could even reveal size of the message. So I wanted to just give an example here. Even when we have like a strong mixing strategy like this, for instance, the continuous time mix, if the packet format was weak, if it was able to like actually reveal the size of the packet, we would just see a large, medium, and a small packet entering a mix node, and then in a different order, a large, medium, small packet exiting out. So we would still be able to correlate it. So this shouldn't be possible with a stronger mixed packet format. And it should also support anonymous replies, because so far in the mix, I just talked about like unidirectional communication, but there should be a way for the recipient to respond back to the sender without learning the identity of the sender. And the way this should be done is the forward message should look exactly like the reply messages. This is again an important property, because if the forward messages and the reply messages were to look different, then based on this, the anonymity sets would reduce, because like mixed nodes would be able to identify which is the forward message and which is the reply message. So for in order to like prevent metadata leaks and enable indistinguishable replies, we use Sphinx cryptographic packet format. Now we will look into Sphinx cryptographic packet format, like what traits does it provide. So Sphinx cryptographic packet format actually ensures that the packet size are constant, and it provides bitwise unlinkability, and we are able to encode the delays into the packet. So what ideally happens is like we see constant sized packets entering the mix node, and constant sized packets at different time intervals leaving the mix node. So and they are bitwise unlinkable, so it would be hard to actually link a particular packet to the incoming packet. And it also hides the hop count, even from the mix nodes. Any mix node in the path would not know like which hop it is in. It would just know the previous hop and the next hop. And this is a compact encoding, and it's computationally cheap. Apart from that, it provides per hop integrity checks, like I'll show in the next slide. So this per hop integrity check stops malformed and spoofed packets from propagating downstream. Like immediately a mix node, as soon as it checks and the integrity check fails, it would just discard the packet. And it prevents endless routing because it has a fixed header structure and maximum path length. So the packets are also fixed size. So it prevents endless routing. The maximum hops that a packet can go to is the maximum path length. And it supports random delays. Like, as I already mentioned, we would be able to encode the delay into the packet. And it has provable security. So now here is an overview of how the Sphinx cryptographic packet format works. So the Sphinx cryptographic packet format has 4 components: alpha, beta, gamma, delta. Alpha is the group element, beta is the routing information with padding, and gamma is the MAC, and delta is the payload. So gamma provides this integrity check. So as soon as a mix node receives this packet, it derives the shared secret S using its own private key and the group element. And once it derives the shared secret, it would be able to check if the integrity check holds, that is, the MAC is valid. And then it adds padding to the beta and decrypts it. Once beta is decrypted, this is how it looks. It would have the full address of the next hop, the node to forward this to, and it would have the delay of how long the mix needs to hold the packet. And then there would be gamma dash and beta dash. And with the shared secret, it would also be able to compute the group element for the next hop and the payload for the next hop. And once it computes alpha dash and delta dash, it again just puts them all together: alpha dash, beta dash, gamma dash, and delta dash. It holds the packet for the delay time, and then it forwards it to the next hop. So with this, we have like the basic of the uh, mix network to continue with the libp2p integration. So as we have seen, like mix differs from Tor, and we saw the 2 key components of the mix. The 2 key components are the mixing strategy and the packet format. For mixing strategy, we use continuous time mix, and for the packet format, we use Sphinx cryptographic packet format, which is constant sized, and it has all the advantages that we just saw in the previous slide. So in case of libp2p integration, there are more components to it. So first I'll talk about the components which are pluggable, like we could substitute it with anything. So the discovery mechanism, delays, spam protection, cover traffic, incentivization, all these are pluggable. So we can replace them with any discovery mechanism, or or delay, or even skip the delay. So in case of discovery mechanism, the discovery mechanism should allow the nodes to advertise that they support mix, that they support, and they should also be able to advertise their X25519 public key for Sphinx encryption. This actually, the public key size is 32 bytes. And apart from that, the discovery mechanism should provide an unbiased random sample of mixed nodes. This is a very important point, because if the discovery mechanism was skewed and it doesn't provide like a random sample of mixed nodes, then an adversary could always manipulate the discovery mechanism to make sure that the the adversary control nodes could be chosen as chosen in the pool of selected nodes. And for delay, currently we embed the delay in the Sphinx packet. We use 2 bytes for it in our implementation. And there are other options, like you could either use a network-wide parameter or skip this delay completely, just have it as 0 zeros. So delay is also pluggable. And spam prevention, this actually protects the destination. This again, we would be able to embed in the Sphinx packet instead of the payload being the size apart from the header. We would add this extra for the spam prevention. And cover traffic is also pluggable. This provides an unobservability. which is much more stronger than unlinkability, in the sense that an adversary wouldn't be able to tell even if if a sender is actually sending messages through the mixed network. This is because the mixed nodes can periodically send loops of cover traffic that start from them and end at them. So since they keep doing this and in between they send the messages, the adversary observing the network wouldn't be able to tell whether uh, the sender is actually sending a message. And incentivization, currently to publish a libp2p message anonymously, the nodes must run a mix instance, and that's the only thing we have. But like I said, we could look into better incentivization mechanisms at a later point in time. So now that we have looked into the pluggable components, we will jump into the major question of whether mix needs to be designed as a protocol or a transport. So where exactly mix fits in the libp2p stack. So it's not unusual to consider designing mix as a protocol or a transport. In case of a protocol, it acts as an overlay network over existing transport. But in case of designing it as a transport, it acts on the further lower level, just like any other transport, like the TCP transport. We found that mix as a protocol provides more flexibility. I'll explain why in the following slides. So the mix protocol, it just takes care of how the message is routed through the mix network. So it takes care of randomized path selection using mix nodes and wrapping of the message into strings packet and then routing it through the mix node. But it does not handle the origin protocol and the mix communication at the entry and the exit. So any message can be forwarded via the mix protocol until the exit, but this message, actually like connecting it with the origin protocol, for that we need an entry interface and the exit interface. That's not included in the mix protocol. The transport approach also has a similar setup, but the reason why the transport approach doesn't have much more flexibility is that in case of libp2p, a negotiated transport applies to all peer communications, but we may need to use the mix for specific messages. Like we want to mixify certain messages and other messages we do not need anonymity. But in the transport message, we wouldn't be able to do this. This property is particularly more interesting for pub/sub protocols like gossip sub, where we do not want to send all the messages through the mixed network. For anonymity, we just want to anonymize the first hop, and for rest of the other hops, we would want to use the regular transport. And libp2p currently doesn't allow us to dynamically switch between transports. So for this, we may need to update the libp2p spec. And because of that, we just go with the protocol approach because it's more flexible. It enables mixifying per message, and mix operates above transport, allowing flexibility. It could use existing libp2p transport like TCP, Quick, etc. And like I already mentioned, we would still have to figure out how we need to design the entry layer and the exit layer. And now, so far, like what we have seen is we have seen the libp2p integration, and for that we saw which are all the pluggable components. Then we saw protocol versus transport approach, and from now on, we will just focus on the mixed protocol. So in mixed protocol, it has the protocol identifier, and every mix node can take one of the three roles given here. It can be sender, intermediary, or exit in any path. Depending on the path, it can be a sender, intermediary, or exit. But the senders are for one node in the sense that they would be present in the same switch as the origin protocol. So the origin protocol forwards the message to the mix instance instead of the destination if it were to mixify the message. And there it requires changes to send bar public function, sorry, publish functions. The send bar publish functions, when they actually need to send a message, they would look at a flag. For instance, you could have something like use mix. So they look at the flag, and if it is set to true, they send it to the local mix instance. Otherwise, they would just send it to the destination directly. So for this, we need to have a callback at the entry layer. And so the sender node, basically what it does is it selects, it chooses mix nodes for a path, and then it creates the Sphinx packet, that is, wraps the message in Sphinx packet and sends the packet to the first hop. And any intermediary node, all it does is it just receives the incoming Sphinx packet, decrypts a layer of the Sphinx packet, and like we said, it retrieves the next hop's multi-address and delay if it was used. It holds the message for that delay amount, and then it forwards it to the next hop. And regarding exit, this is where we have two options. One is exit is the destination, or exit forwards the plain text message to the destination. Now we will see these two options in detail. So the first option is exit as the destination. So the way this works is the mixed protocol instance at the exit can reside in the same instance as the origin protocol of the destination, or it could reside in the different instance. So if exit is the destination, the mixed protocol instance resides in the same node as the destination. So what happens is the sender's origin protocol sends it to the mixed protocol, which sends it to its local mixed protocol instance, which then routes the message through the mixed network. And when it reaches the exit mixed protocol instance, the exit mixed protocol instance should have a way to invoke the origin protocol handler. And this has one drawback, this option of exit being the destination. The destination must support the mixed protocol, and it requires an exit abstraction, which would invoke the origin protocol handler. And the next option, which is that the exit is not the destination. Here we have a major advantage. The destination need not support mixed protocol because the exit mixed protocol resides in another instance. But the exit protocol removes but the exit node removes the last layer of encryption. So it actually sees the plain text message. And here, if the exit actually makes a client-only connection to the destination, it need not support the origin protocol. So the way this would work is the message would be sent to the local mixed protocol instance, which routes it through the mixed network. And at the exit node, the exit mix instance would see the plain text. It then sees the destination embedded on it. It would forward it to the destination protocol instance, like the origin protocol instance, by making a client-only connection. And now we have seen how mixed protocol is integrated in libp2p. Now we will look into the reply mechanism using single-use reply blocks. This is currently not in the RFC, but so far everything we have seen is one-way communication in the mix. We didn't see response. So even in the implementations, we have no response ping. That is, you would be able to ping a destination but not get a response back. So here I just wanted to say how, if we were to support reply, how we could support and the challenges with it. So SERBs allow anonymous responses back to the sender. This is from the original Sphinx paper. So the mixed protocol currently in the current state doesn't support SERBs yet. But how the SERB works is sender encodes a SERB and attaches it to some anonymous message. The destination doesn't know the sender, but it can use the SERB as the response address. So it would, when the destination wants to respond back to the sender, it takes the message, attaches the SERB, and then it forwards it to the first node, first mix node. And after that, it is exactly like the forward message. Each mix node would just unwrap one layer and forward it to the next node. The sender would have encoded it such that the sender would be able to receive this message at the other end. The reply is routed through the mix network back to the sender anonymously. The recipient doesn't cannot identify the sender in this process. So the challenge is that the origin protocol at the destination is oblivious to serve, because it's just going to send a response. It doesn't know that the existence of the serve. So it would just send the response to its mix instance. The mix instance at the exit must map the serve to the response. So here again, we can look into the two options which we had earlier. The exit is the destination and the exit is not the destination. So in case of exit is the destination, we need to use some context like the ephemeral ID to associate reply with the serves. Here, the exit lives on the exit mix instance and the origin protocol instance are part of the same node. So there should be some way to actually map these ephemeral IDs when the response come. So one way would be it could embed this ephemeral ID in the exit abstraction that we currently have. But this is to be further explored. And in case of the second option where exit is not the destination, it would be easier. It only requires state tracking. So the exit nodes in this case, the exit node does not support the origin protocol. The destination node does not support the mix protocol. So the exit would, like we mentioned earlier, the exit would just open a client-only connection to the destination, and the destination would respond back through the same stream. So in this case, exit could just maintain a map of the stream ID to the serves, and then the exit mix instance could use the serve to actually forward it through the mix network. So far, we have seen the libp2p integration, and we saw the advantages of like the protocol approach over the transport approach. And we talked about how the mix protocol interacts. And then we looked into anonymous replies using single-use reply blocks. Now we will look into some known limitations. So in case of mix, there is no mechanism to identify bad behavior. That is, mix nodes can be unreliable. They can delay, drop, or selectively forward packets. But currently, we don't have any mechanism to identify this behavior. And there is no built-in retry mechanism. So if a mix node fails or is unavailable, the message is lost. It's just lost. So we just rely on the sender sending the message via D paths for reliability. And mix doesn't inherently defend against Sybil attacks. So it's easy for nodes to actually spawn multiple nodes. But I just wanted to this is not as such a protection for Sybil attacks. But even if that was rewired to control 1/3 of the network, the de-anonymization probability is just 0.3. 1/3 of the network would be like super large, but still the de-anonymization probability is less. This is a work in progress, the calculation of the probability. And mix doesn't inherently defend against large-scale DOS attacks. Like there is no protection for DOS against these mix nodes. But I want to point out that the Sphinx cryptographic packet format resists tagging attacks. And the per hop integrity checks stop malformed or spoofed packets from propagating down the stream. Random delays and dummy traffic, if we introduce it, resists timing and traffic correlation. So because of these properties of Sphinx cryptographic packet format, it would be much harder to launch like targeted DOS attacks. And with this, like the libp2p integration of mix is over. Now, I quickly want to go through the gossips of the integration. This is a work in progress. So gossip sub is a pub sub protocol, which is based on randomized topic-based meshes and gossip. Here, I just wanted to like uh, quickly overview the different types of peers in Gossip Sub. Of course, I have missed out like direct peers. It's not like a full overview of Gossip Sub. It's just enough for us to like see how the mixed protocol would be integrated with Gossip Sub. So peers connect via full message or metadata only peerings. So full message peers basically transmit full contents of the message, and usually this is sparsely connected. We refer to them as mesh peers as well. Each peer is connected only to 4 to 12 other peers, with 6 being the default. And there are metadata only peers which just gossip about the available messages. These are densely connected. All connected peers that are in full message peers would be metadata only peers. And there are fan out peers. Fan out peers are used for publishing to non-subscribed topics. They randomly pick 6 peers that are subscribed to that topic, and those 6 peers would be set as the fan out peers. And these fan out peers is unidirectional, while the other 2 kinds of peers are bidirectional. So in case of in case of Gossip Sub mix integration, what we do is when initializing Gossip Sub, we pass a callback for the mix entry layer. So what happens is every time when a message needs to be published to a topic using the mix, where we pass a flag saying this message needs to be routed through the mix network. At that point in time, since we had already initialized Gossip Sub with this callback, the callback would be invoked. So what exactly is being done here is the peer selects random D peers from all known peers subscribed to the topic, and then it routes the message to these D peers through the mix network. So D typically is set to a small number like 3 to 4 to balance reliability and anonymity. So we would be able to like later see how we can actually like fine tune different values of D for desired reliability and anonymity. And the message is published via the mix protocol. So the key implications is that it enhances sender anonymity in Gossip Sub. It maintains efficient message propagation, and it allows tuning of, like I mentioned, allows tuning of anonymity versus reliability. And here is a pictorial representation of it. The sender anonymously publishes to D peers subscribe to the topic via mix. So it just chooses random D peers and then sends the message through to them through the mix network. And once inside this topic, the message propagates to all other subscribers as usual. And here is the actual integration flow. And this integration flow is already implemented. And for this, we have used exit as the destination. So it does have the drawback that the destination needs to support the mixed protocol. But we chose this because in case of Gossip Sub, at least in the NIM implementation, even though this is not a issue with the spec, in NIM implementation, we are not able to make like client-only connections to the destination. So because of that, we have chosen this option. So the Gossip Sub protocol would actually send the message to its local mix protocol instance, which then routes it to D peers through the mix network. And at the exit would just invoke the Gossip Sub protocol handler. And with this, we have finished the Gossip Sub integration as well. And now I would talk about the next steps. So benchmarking anonymized Gossip Sub, evaluate performance overhead and message propagation efficiency, and mix Waco integration. The Waco team is working on integrating mix with light push and stored protocols. Anonymous replies with SERVs. This is the next step. Like we need to implement the single-use reply block that we actually saw for anonymous responses, and RFC updates from community feedback, like from WAC forum discussion, we got extensive feedback. And also there were a lot of like implementation learnings. We want to incorporate it into the RFC. And with this, we are at the end. So to summarize, the MIX protocol provides sender anonymity support for libp2p. So we have the Sphinx packet format, which ensures unlinkability with fixed size packets on layered encryption. And we have the random path selection. So the messages are routed through a random series of mixed node concealing the origin. And seamless integration. It works with existing libp2p protocols without requiring modification to their handlers. It only requires changes to the send bar publish functions. And it's pluggable and extensible in the sense that like I mentioned already, the discovery, delay, spam protection, cover traffic, and incentivization, everything is pluggable. And with this, that's it. Thank you.
Yeah, thank you very much, Akshaya, for this very thorough summary of the research that has happened so far here. So yeah, let's open the floor for questions. Yeah, Hanno.
Cool. Yes, I probably have a couple of questions, but I'll see which ones I remember. Thank you very much, Akshaya, for not only this research but for the presentation, which was very informative. Quick question from my side: what do these SERPs actually look like? Are they sort of pseudo addresses that you respond to and you just correlate them internally, or?
No, it's just like so it's going to be a node and like an encrypted packet. You can just attach the message to it. So there is a way you can attach the message to this. So once you attach it to the SERP, you have to send it to the first hop, and after that, it looks like the processing would look like an exact Sphinx packet. So the first node would receive it. It would look like a Sphinx packet. It would be oblivious to the fact that it's actually it's a response and not a forward message. It would be oblivious to the fact, and it does the usual processing, like remove a layer and then forward it to the next mix node. So the way this is done is the sender of the message, they would actually make sure that to choose random nodes for the return path. And then they would come up with this SERP, and then they send it with the message. But these SERPs can be used exactly once.
Okay, that makes sense. So that would be, in a sense, that would be the SERP would contain the return path, right? So to understand that,
yeah.
Okay, that makes sense. Thanks for that. Is it okay if I ask another question? I don't want to take anyone else's time. Cool. Okay, I'll go ahead. Then the other thing that you mentioned was that there's a drawback of using having the exit node not to be the destination node as well, is that you would have the final message in plain text, right?
Yeah.
Is this completely inevitable? I assume you would need to know what protocol stream to create to the destination node, but I assume we could introduce another layer of encryption there.
We could actually, initially we were talking about the noise encryption, but it's just that these encryptions would be end to end, right? It would be between the sender and the destination. They would need to actually exchange a key and then do this encryption to have for us to have this another layer of encryption. But that's not straightforward, because with the mixed protocol, there is no multi-stream negotiation. They wouldn't be able to negotiate keys beforehand for them to encrypt this last hop. So that's something we still need to figure out. So if there was a way for the sender and the destination to exchange keys beforehand, they could use them to actually encrypt the message and send the encrypted message via the mixed method.
Yes. Thanks. Yes, that makes perfect sense. I can imagine it's not trivial, but I was just wondering if there's any other fundamental reason. Yes.
Yeah.
Yeah, maybe just adding to this, it's just plain text from the mixed view, and then for specific origin protocols, it might be fine. Let's say if the sender and the receiver already have a pairing, they could derive keys from that. But again, that depends on the protocol that's actually tunneled via mix.
Yeah.
So yeah.
Yeah,
So
absolutely.
that's not a restriction at all. It's just like from the mix
Yes.
view. And then, so as like Shaya said, like solving this generally, that's more difficult. If we assume that sender and receiver do not have any pairing as of yet, then this is more difficult, but that's also part of the future research.
Yes, thanks. That makes a lot of sense. Yeah, I don't want to take up any more time. Go ahead, Leonard.
Yeah, I've got a simple enough question. In terms of optimizing this, is there a minimum number of mixing hops that we go through, or is it going to be configurable that you can actually you can say, well, actually, I need some optimization, and I can actually work with a reduced mixing count?
We could definitely work with a reduced number of hops, because both of these, like I said, the Sphinx packet, it has a specific structure. So we have to beforehand actually like say what would be the maximum path length that we would tolerate. And at any point in time, the minimum path length would be 3, because only with 3 nodes, like we would be able to provide sufficient anonymity. So between 3 and the maximum path length, it's configurable. Like the sender could choose any number.
Okay, and I've got a follow-on question, but it's actually, Corey, thank you for answering regarding Nomos. In terms of one of the things we're looking at the moment is the neutrality stance on the Nomos side and trying to articulate that. Is there optionality for mixed nets to have almost like pseudo levels of mixing, so you can actually flip it? Is it an easy selection to remove the layers, or is it just a on-off switch?
Sorry, I don't understand this. So you're sorry, I don't follow this. Like you're asking if we are able to like select.
It's either on or off, I guess. Yeah, it's either on or off. I mean, one of the things we're looking at is
you can on or off it like per message, or that's
okay.
how we are integrating. But it depends on the entry layer and the exit layer that you configure for each protocol. So in the entry and exit layer, ideally you would have like a separate send function for the mixed protocol, and there you could have just a flag like which would say on or off, and based on whether it's on or off, the messages can be routed through the mixed network or not.
Okay, thank you.
So maybe just adding to this from the protocol, that's actually like the original protocol point of view. It can be selective. It has been, as Akshaya said, it has to be implemented in the entry and exit for this protocol. But let's say for gossip sub, only the first hop would be going over mix. And we can even do it for select messages within gossip sub, but not for the relay parts. So from the point of view of the protocol that's tunneled through mix, it can be selective. And the user, let's say the API for that protocol that gets tunneled, the API that Gossip Sub offers to a client node, they don't have to know that. They would just use Gossip Sub, and the messages that originate, they would go through Mix, the others not.
Gotcha. Just the use case for this is, let's say you're using your network for micropayments and you want it to be really fast, but in another situation you want to have the ultimate obfuscation security. You want to be able to optimize. That's what I'm thinking about. Thank you.
Yeah, you can do that. Yes, you can also expose it. You can also expose this to the client API. Yeah, that works as well. Yeah, Jess.
Perfect. So I saw that there's a constant size payload in order to hide the data for traffic classification. I'm curious what kind of factors might go in to choosing the optimal size for that, assuming that I was correct in understanding that it's a constant size payload, not a header.
Yep. It's a constant size payload. We actually like do padding, but it depends like based on based on how much padding you want to add. like how much small messages the application need to send. Based on that, you could actually choose the perfect packet size.
Thanks.
We also adding just like that, this like the content size is also an important factor in preventing specific denial of service attacks. Like Shai mentioned that in the talk, but maybe just to repeat that, you know, with this you can prevent malicious packets that would just loop through the network basically infinitely. So if you say you have a hop count of 3, then you would enforce a header size that exactly fits 3 forward addresses, and you enforce a certain body size, and then an intermediate node can check that it is within these constraints and will drop the message if the body would contain further hop information. So to have that's kind of a trade-off to get this very simple denial of service protection here, or mitigation rather. You need to have the constant. You have to have a fixed packet size.
Point of clarification here is that, once again, I would sounds like that's on the header fixed size, right? If you want to limit the number of addresses or hops that can go through there, or are we still talking about, in fact, of fixed payload size as well?
Even the body has to be fixed for that.
Yeah.
Okay.
The entire structure is actually fixed. You have like a specific alpha size, a beta size, a gamma size, and a delta size. So everything is fixed, and overall it's constant sized as well.
Perfect. That makes sense. Thanks.
Because if you would not fix the body as well, I mean the full payload as well, you could basically put further information into that. You know, like the intermediate hop doesn't know that the header has already been processed. So it just gets a message and thinks, okay, the first few bytes, this is still part of the header. But the body, or like the payload has to have a specific size so it can check, okay, this is too small now, I will drop it. It has hopped too many times. Yep, from...
Hi. I think my question is also related to the packet size. In, like, for example, Waku network, the public Waku network, at least, we, I think, have defined a packet size of, max packet size of 150 kilobytes. But what we have noticed is that different applications building on top generally tend to use, packet size that falls in different ranges. I mean, we could have applications that may just use 1 KB packet sizes, let's say simple chat apps, which are using just text-based messaging, but there could be apps that may be using, let's say, 50 KB packet sizes. How would you recommend, we define what should be the mixed packet size in this case?
Actually, like, this is something we would need to explore a lot more. But it's just that, like, one thing I wanted to point out is we cannot have like different packet sizes, because that itself would reveal like which sort of applications is being padded to that. Like if a packet size, if we were to say that like packet size less than 50 KB would be like padded up to 100 KB. So we would actually know that like all these 100 KB packets are of applications that are using where the message size is less than 50 KB. So we are actually indirectly reducing the anonymity set for these, depending on the application. So based on the application, if this was like an okay thing, like if it was a good trade-off to do in terms, because you would be using lesser bandwidth, in case of that, we could go with it. Or otherwise, just using like one packet size, like one big packet size with all of them padded would be the best approach from anonymity point of view.
Okay, got it. Thanks.
Alexander.
So thank you for the presentation, but unfortunately I missed part of it, like the beginning. So my question is like, probably you mentioned this somewhere. And my question is, are you actually using here like a dummy messages in this protocol?
Sorry, what messages?
Are you using like a dummy messages, like?
Oh, dummy messages. Yeah, like currently, like we do not have any covered traffic, but like I mentioned, covered traffic is pluggable. So you could have covered traffic, like depending upon your application, you could use decide to like have covered traffic and also the frequency of the covered traffic. So the covered traffic would actually provide a more powerful property of unobservability.
So is it true then to say that if we don't use a cover traffic, then the anonymity properties offered are kind of like equivalent in some sense to the Tor anonymity, which is known to be broken? Is that true?
No, in Tor, like you would be able to perform like volume attacks and traffic correlation at the endpoints based on the timing. That would still not be possible here. Like if you were to use only this unobservability property will not be there, but still it would provide complete unlinkability. And until the destination, you wouldn't be able to correlate the message based on just the size or volume.
Yeah, because in my understanding, this traffic of dummy messages, it's like important, right?
Yeah, it's
in order to prevent basically, from the, like traffic analysis and things like that.
Yeah, that's what, like I mentioned, you would know, like if the dummy messages are not there, you would know like when the sender is actually sending messages. But if you had dummy traffic, that's the protection it adds. You wouldn't be able to say like when they are actually sending messages and when they are actually sending just dummy traffic. So you wouldn't know like through the network, like when there is real traffic and when it's just dummy traffic. But if we don't have the dummy traffic, you would know that it's always real traffic, but still you wouldn't be able to correlate it because like I mentioned, for every mixed node, the incoming packets and the outgoing packets look exactly similar. They are just timed differently and they are unlinkable. Like you have bitwise unlinkability. So you would just see Sphinx packets going through mixed nodes and a bunch of Sphinx packets coming out of the mixed node. And it's hard to actually correlate them.
Okay. Also, at some point of your presentation, you mentioned those estimates of the probabilities of the de-anonymization, I believe.
Yeah, I did. I believe in the known limitations, if I'm right.
Yes. Oh, yeah. Okay. So just so the way you just like to understand the way you calculate this, because let's say I understand that the user who sends the message, he chooses the path, right?
Yeah.
And you have a number of the nodes on this path. Let's say 3, 5. I think 1. It's a minimum one, right?
Yeah. So this is, I don't know, like if this is your question, but this 0.3 is calculated with a 3-hop path.
Okay, so it's a 3-hop, so it's a 3 mixed nodes basically.
Yeah,
right?
3 mixed nodes. Yeah,
and then it's a probability basically that all of them are adversarial. That's the probability you give here.
That's the probability. It's a bit complicated here because from the entire mixed node in the network, you're going to like select only a part of them and you're going to have it in your cache, and from the cache you would choose, but it should actually mimic the probability of like choosing nodes uniformly at random from the entire network. And if we are able to achieve this, then the probability would be this 0.3.
Yeah, and so maybe the last question, if I may. So in the end, you mentioned basically like next things to do, like, and one of them, I think it was, I believe, like testing, I don't know, various properties, like performance overhead, message propagation, efficiency. So this is, I understand, like, I don't know, measuring like a bandwidth and latency, right? How do you going to measure also like anonymity properties of this?
That's a good question.
Because they have to be also evaluated somehow, right?
Yeah, that's a good question. But like since Sphinx cryptographic packet format like theoretically provides all this. I would say like if we had implemented it properly, unless like there is something wrong with the implementation, it would have these properties. So really like
but
yeah.
I think this is not enough. Just Sphinx encryption itself, it's not enough, right?
Yeah.
So
Just
we
to-
will definitely work on. So
Yeah.
this is definitely also on the list, a thorough analysis of the anonymity properties, and we also make some compromises, and to get to a minimum value, minimum viable product as soon as possible, and then we will improve anonymity properties from there on. But this is definitely part of it. So a part of the future steps.
Yeah. Okay.
Yeah.
Thank you.
But as I mentioned before, so like one of the first, benchmarks is kind of is Tor and getting better than Tor, and as Akshaya explained, so we can defend against these correlation attacks. So this is kind of the first step, but then thorough analysis, this is something that will follow.
I mean, the way I understand, basically, like in order to kind of to step away from Tor in a kind of a better direction, one needs to add dummy messages, and then that's on.
Yeah, but even without, as Akshaya said, even without dummy messages, you have the protection against correlation attacks. So this is huge, actually. So it's definitely a stronger threat model that this would still protect in compared to Tor.
It's kind of, I mean, it's kind of true, but then one needs to kind of to measure those correlations somehow, right? To quantify, like, I mean, let's say, and for that you need to assume adversary and what he does. For example, if he does some sort of like a statistical analysis,
Yes.
that basically that he cannot do this analysis like in a reasonable time, basically.
Yes, yeah. But again, so like for us, like the main thing is to get this out as a protocol in the peer-to-peer, and it's definitely improving on the status quo. And then we would add this analysis plus improving security properties. So one thing is surely is true is if there's no cover traffic and the message rate is very low, then you can still correlate. That's true. So there's definitely we need to analyze these properties.
But that sort of an attack would be possible like everywhere. So we would assume like a sufficient number of mixed nodes and sufficient participants being there. Like that would be like basic property that would be required out of all mixed nodes.
Yeah.
So all mixed networks. So that's the assumption I took, like when I was saying like even without unobservability, it has like a stronger anonymity model. But definitely, like if the traffic is low and if the number of mixed nodes is low, like we have a problem there.
Yeah. But again, this is kind of improving the status quo, like incrementally. This is kind of the goal of this effort. Because for now, we have Gossip Sub without any protection. This was kind of the main protocol we wanted to anonymize. And then moving towards Gossip Sub anonymization, we thought, okay, it makes more sense and is even more useful if we do this as a general peer-to-peer protocol that you can anonymize all the protocols. And improving from that is kind of the goal here. Yep. Daniel?
Hey, so how is this going to be played? Because from my understanding on how libp2p is designed, it's a bit intrusive that if another protocol needs to use this protocol, we will push some changes in the specification of the other protocols. That seems a bit weird, right?
No, like you're not actually changing
Or
that.
I understood it incorrectly, maybe, yeah.
No, you don't require actually change to the handler of these protocols. You just need a change in the send or publish functions. This is sort of unavoidable because at some point you need to say, like, instead of routing it the regular way, route it through the mix network. Like whenever I switch on something, you want to route it through the mix, and whenever I switch it off, you route it regularly. So that needs to be added somewhere. So that's where, like, we have this entry layer and the exit layer. We try to make this entry layer and exit layer as much as possible usable with all the protocols with minimal changes. That's something we have been trying with the entry and the exit abstraction. It's not completely successful, but yeah.
Oh,
Let's go ahead. Yeah.
okay. So the idea is to actually specify this in and outer layers, right? And then get it incorporated to integrate with the other protocols. Yeah, that's
So
that's
the
cool.
entry layer, basically what it does is it creates a virtual stream to the local mix instance, and it would call the local mix instance send function, like the send function to route through the mix network. And the exit layer at the other end, it would invoke the handler on like a buffer. Basically, it would store the messages. The mix instance would store the message in a buffer, and then would have like a virtual stream to the origin protocol, where the origin protocol can read from the stream. But
Sure.
yeah, at a later point in time, we want to explore like better mechanisms for this entry and exit layer, where we actually like have like introduce like separate abstractions which would do these things.
Cool. Sounds nice. Thank you.
Any more questions? Yeah, so then in this case, let me thank you again, Akshaya, for this very informative presentation. Also, thanks a lot to the audience for the questions, many interesting questions. I also wanted to point out that we have an ongoing discussion in a VAC forum also around the specification that helped a lot to get input. Thanks to the Waku team for being active there, but maybe we can even get more input and get this discussion going there. Thanks for that. And so next week we are planning to have a sorry, not next week, I mean the next slot, which will be in 2 weeks. We will have a call planned with Nimbus and on large messages in the peer-to-peer and Ethereum network. It hasn't been confirmed yet, but you will find it in the IFT research call schedule as soon as I get confirmation on that. Thanks again, and see you in the next call. Thank you.